Okay, guys, please make sure you learn from your mistakes on the quizzes. Don't make the same mistakes on the tests. Let's see, lab. I didn't bring my list, but list of things for lab. Please remember your dress. I think I did not see anybody that was dressing perfectly. Ankles need to be covered, okay, but look pretty good. Things that were not good, test tubes. Test tubes are returned, not rinsed with acetone. Wednesday. So that means for the Thursday test tubes were not dry. I had to scramble and find dry test tubes. The water will not dry out of a test tube overnight. It takes about a week or two. Okay. Please read washing glassware. Okay. How to wash glassware. Yesterday people were putting tape on things for labeling. Don't use tape. Okay. Well, the tape will never come off if you leave it on there more than a day. Then it'll just be stuck on there and stuff. And just write directly on glass with Sharpie marker, and then it will rinse off with acetone. Might require just a touch scrubbing with a brush, and it'll just come off. There was one more thing. I forgot my list. Signing in and out. Time in, time out. Upon writing time out, you initial. A number of people did not do that. So now there's one more thing. Questions about lab coming up. You got the out of lab worksheet exercise focusing on SciFinder, no lab on Monday or Tuesday. Questions about the sheet? Thus far, questions?
For our formal lab report, do we turn it in, like, print it out, or do we submit it online?
No, you turn it in and print it out, and those are due, your solubility lab report is due Wednesday, Thursday, when you come to lab. Yeah? Print it out. Guidelines for reports are in the lab manual. Any questions, please ask. Any questions about the SciFinder assignment, please ask. That's due Friday, June 2nd, yeah? Okay. Now, when you come to lab next Wednesday, Thursday, we're doing, I believe it's unknown. Termination of an unknown, is that right? Okay, that will involve a distillation. There is a video demo of the distillation on the YouTube page. That is a fairly long lab. It'll be kind of your longest pre-lab. Of course, you can, you don't have to write every single word. You need to be able to work from your notebook. If so, then you're probably going to be good. Need to watch the video for distillation. Okay? I'm not going to discuss it when we get there. That will be a longer lab. It'll take, as it's written, it's probably going to say a week and a half. That's during the regular semester. Okay? Here we have longer labs in the summer. We're going to do it all in one lab. Okay? Regular semester, I'll give a week and a half. For us, all one lab. Okay, other things today before we begin. Yes?
What from chapter 15 is the IR? That's the only thing covered?
IR will be on the test. There's a video. There's 2 videos. There's problems in the workbook. Any questions about IR?
No, my question is that the only thing from chapter 15 that will be on the exam?
Chapter 15 is also, I think, mass spec. I think so. Over there, the only thing over that way is IR.
Okay.
I think mass spec is in the same chapter. Mass spec we'll cover during test 3.
Thank you.
Anything else? Okay. Let's get started. I think we can go back to the acid base a little bit. Nomenclature by video only. Yeah, how we doing nomenclature? Okay. On Tuesday, we'll perhaps do a couple of IR problems in class, see what type of questions are about IR. We may do that nomenclature today when we go over to the other handout, that one that was not done. Okay, I think we can pick up here. We did this one in class, right? The one below. We have outcome for this. The most acidic H on the board, these are all CHs. We got this OH here. I'd rather make Ni in here. There's your acid proton. This guy's going to be the base. Okay, it's sp2 nitrogen. Okay, let's draw the bond in here. Yeah. These electrons attack H. These electrons stay here, and we're going to get. This is called pyridine. It's a benzene ring with one of the CHs replaced with a nitrogen. That's now bonded to an H. Lo and behold, that's a positive charge. Whenever I draw in the three bonds of such a ring, they may not be quite precise. But please note it's boom, boom, boom. Okay? Well, the other's a benzene ring. So that's a pyridine ring. The other is the phenol. And what does this look like?
3 lone pairs.
3 lone pairs, right? I mean, right here, you started with 2. Now, these electrons move on to the oxygen as a third. It's the same old mechanism. There's your ion pair that we have. Okay, which side's favored? The acid over here. It's a phenol, pK of about 10. What's the acid over here? Which species has the proton? If I put the proton in red, that would be red and this would be red. There's the proton. What's the pK of this guy? 5. Because, hey, this is a base. It's acting as a base, so why are we giving a pKa? When you give a pKa of a base, it's actually referring to what? Conjugate acid. There's the conjugate acid, pK of 5. Okay, we got 5 and 10. Which side's favored? Side with the weaker acid, which is what? 10. So actually this side is favored. Okay, it's more like that. Starting side is favored. That means it's not going to go that way much. Question, is pyridine strong enough to fully deprotonate this guy? And go that way? No. It's not going to do it much. I mean, the equilibrium is the difference of what? 5? At equilibrium, you have 1 of these and 10 to the 5 of these. So at equilibrium, you got, what is this, 100,000? Only 1 out of 100,000 is deprotonated. Pyridine's not a strong enough base to do this. But that doesn't mean we still can't show the acid-base reaction that would occur, that's most likely to occur. Yeah? Same as above. How about the one below? Questions about that one? This one down here, the acid and the base are in the same molecule. This is an alpha amino acid. That's a carboxylic acid. First carbon is called the alpha carbon, and on the alpha carbon we have the amine, alpha amino acid. Well, these are your protein building blocks. There's 20 common amino acids. You may be learning some of these. Serine, threonine, methionine, arginine, I think, things like this. They just differ from the R group that's on the alpha carbon as well. Show the reaction. It's only one molecule. But again, it has 2 reacting species. If you want to just pretend like it's not connected, you can do that. What do we have? What's the most acidic H on the board? Why the OH and not the NH? Oh, you're looking at pKa. Okay, well you can, it's up there, but if you didn't have pKa's, how would you know?
Oxygen is more electronegative.
You'd rather make anion on oxygen than anion on nitrogen.
Well, can't you also say because of carboxylic?
Yeah, it's also, it's called a carboxylic acid. Yeah, it's acidic. Okay? Yes. Not only would the anion be on oxygen, but it would also be resonance stabilized because one of the lone pairs would be in a p orbital. So the lone pairs that are there would have something to do. This would be on a less electronegative atom, and it would not be resonance. Yes, that's the most acidic proton. And its pK is 5. That means, okay, so what's the most basic atom on the board? Anions and sp3 nitrogens are good bases. So sp3 nitrogen, yeah, that's your base. Okay, do the reaction. Well, this may not, the mechanism may not be internally. The mechanism may actually be intermolecular, where the base reacts with the acid of another molecule. Okay, because it may be hard for this guy to reach over here. 1, 2, 3, well, it could. But this could also react like this.
Is that an SP3 or an SP2? It's an SP2.
It's sp3. Did I call it 2? It's an sp3 nitrogen.
No, why is it 3 and not 2?
It's got 4 regions around it, and there's no reason for there to be an exception. So ultimately, in the product, this nitrogen is going to become protonated. And how's this guy going to exist? It's going to be the anion. So we're going to get anion after the base took the proton, right? And the nitrogen is going to look like what? Instead of 2 H's, it's got 3, and lo and behold, that's a positive charge. That's a result of the acid-base reaction. Okay? pK of 5, what's the acid on this side? Where's the H? It's here. What's its pKa? 10. Because the pKa of a base is actually referring to the conjugate acid. 5 and 10, which side's favored? Yes. This is favored, right? Favored by 10 to the 5. This side. So look at this. Here's the amino acid with both functional groups drawn in the neutral form. But guess what? That's not how it's favored to exist. They actually exist like this. That proton sits over there with the nitrogen. This is the favored way for it to exist. Now, assuming the pH doesn't influence this, okay? Dissolve it in pure water, it'll exist like this, okay? And this has two different, it's net neutral, 2 different charges. What do we call such a compound that has, it's net neutral, but it has charges? General name starts with a Z. Yes, Zwitter ion. You ever heard of Zwitter ion? Okay, well, you heard it from me first. Zwitter ion, right? Yeah? Okay. That's how amino acids, right? Everybody there? What are we doing differently here? It's the same as the 3 above, right? Because we have a process of evaluating things. There you go. So we call it internal acid-base reaction, size favored.
How do you know it's favored by 10 to the 5?
Well, the weaker acid's favored. Well, that's a statement we made. We could get into that for an hour or 2 if you want. Okay? I mean, it's just favored. Everything is going, okay? It should make sense if we start looking at it. So this is favored by how much? It's the difference of your pKa units, right? You learned that in Gen Chem? The difference is 5. Okay? This is favored by 10 to the 5. You can do all the huge math that I know you've done before, but hopefully you realize that you can just tell the answer by looking at the pKa's.
Okay.
Okay, Henderson-Hasselbalch. What was this over here? Anything to look at over here? Codeine. If codeine is given, it's going to be given as codeine hydrochloride. That's where the codeine has been reacted with HCl. Most basic atom in codeine. Okay, as we said 30 minutes ago, good bases are what? Anions or sp3 nitrogens, sp2 also slightly some bases. I don't see any anions up here, but I do see an sp3 nitrogen. There's your base. That's your good base. Reacted with acid, protonated. There it is. It's a salt. That's the end result. Hydrochloride salt. Which side's favored? And we can do this. Which side's favored? Well, what's the pK of ACl? It's like -5. You'll see that vary. It's negative something. So that's the starting, right? Down here. What's the peak? What's the acid, conjugate acid down here? This or right or left? Left. This has the proton. What's its pKa? I'm telling you this here. That's the pKa of an amine. If you look at the table in the back of the lab manual, it'll say about 10. It can vary a little bit, 8.8. So which is favored, -5 or 8 or 8.2?
8.2.
8.2. See, this is favored. Reacting with ACl, it's going to be this. But hopefully that makes sense, because HCl is a strong acid. It's going to protonate something kind of fully. But you can see it in your numbers. If you treat this with this, it's going to be like this. Now, practical extra information here. Coating hydrochloride is a solid. How do you get this? Dissolve this in a solvent, you add some HCl gas. It may precipitate as this. If it doesn't, you can evaporate the solvent, and you'll end up with this in the flask as a dry solid. And it will be in this salt form. Just like sodium chloride. Those two ions would be in the salt form, dry solid. Another reason drugs are made or often given as salts. This may be a little low melting, oily. Things that are low melting often are not that crystalline. So they could be oily, not a good solid. If you want to make this into a tablet, you kind of maybe want a good solid. Which is going to have a higher melting point? The free base or the salt? Higher melting point. This. Ionic is going to make it have more IMFs. It's a very strong IMF. This is probably more crystalline, more of a solid-like. Okay. Application of the things we're doing. Oh, over there we can do a little, there's some Hasselbalch. This is aspirin. Aspirin has this carboxylic acid. What functional group is this down here? It's kind of upside down and backwards. If under my hand was an H, that would also be a carboxylic acid. But instead of the O bonding to the H, it's bonded to a carbon. This is on the quiz, too. Ester. You see the ester?
Yeah.
It's just upside down. It's just upside down or whatever, but it's an ester. Here's the acid. Here's the conjugate base, if it acted as an acid. Which form is favored at pH of 6? Left or right? What do we need to know here? Which form is favored at pH of 6? Left or right? What do we need to know? You need some more information before you can... What do we need to know?
Concentrations.
What? No, you don't need concentration. You need what? You need pKa of what? Of this guy. What's the pKa of this? Carboxylic acid. About 5. Will that give us the answer? It will. I'd say maybe 4. 4 to 5. Okay, its pKa is 5. So at pH of 6, which form will predominate? I'll let you do this on your own, and maybe we'll look at it on Tuesday, it doesn't seem like we're ready to look at it today. Have I got the answer?
Yeah, it's gonna be the left side, right? So if the,
No, I'm not sure it's the left side.
okay, yeah, so it's the right side.
Please look at that. Okay, acid base. Okay, let's look at the alkane, cycloalkanes. I don't think we named this one on the video over here. Did we name this one on the right in the video? Okay, let's name this guy on the right. We named this one, I believe, yeah? Longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Hold on. 1, 2, 3, 4, 5, 6, 7, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 straight through there by coincidence. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think there's another 10. Anybody named this yet? I think right through there, by coincidence, is 10, which is what? Decane. We have a decane. If that's all we had, it would be decane. But we have something on the decane. We have this group and this group. This group's the easiest. What is this group? So 1, 2, 3. Propyl. Because when it's a substituent, we don't call it a propane or a propanol. It's shortened to the YL, propyl. It's a straight chain propyl. By the way, here's this down here. I called it kind of a common name, only just to really to compare to the other ones. The N means normal. Normal means straight chain. Okay. What is this guy up here? First off, you number these substituents. The first carbon coming off the mother chain, the main chain, is 1, 2, 3. You find the longest here. It's almost like we're naming it as its own thing. The one position by default is coming off the parent. So it's a propyl. That's the longest. So that's a propyl, just like this. But this propyl has something on it. At the one position, there's a methyl. So we want to write that. 1 methyl propyl. All one word. So 1 methyl propyl. Now that has a common name, which is what? Sec-butyl. But sec-butyl is a common, not IUPAC. IUPAC we want to stick with like this. It's called sec-butyl, by the way, because it's a little bit misleading. Because that carbon is if you've ignored the parent, that carbon is secondary. That's why it's called a sec-butyl. A little bit misleading. Ultimately, if you include the parent, it's a tertiary carbon. There you go. Those are your two substituents in the decane. Numbering. Which end is the 1 in? Well, if this is 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Either way you go, you get 5, 6. You want subs to have lowest numbers. But you got two choices of 5 and 6. Which is how we're going to decide which to give. It'll just be alphabetical. If there's a tie, you just do it alphabetical. Okay? So alphabetical, P and M. M would come first. So it is 1 methyl propyl. Hold on, that's the substituent. Where is it at? Let's number this. M comes before P, so we want this to come before that. So this is 1, 2, 3, 4, 5, 6. We let that be 5 because M comes before P. So at the 5 position, we have dash this thing, which we're going to put in parentheses. That's called a complex sub. It's a sub with a sub. The 5 position, we have that beast. Then at the 6 position, we have propyl and decane. Now, decane, you don't put a dash between that. That just becomes one word through there. And did we get it right? How's it look? Question?
If the last, substituent, is that easy? Okay, if the last one before the chain name is like methylpropyl, do you do like methylpropyl decane? Or do you do a dash then?
You mean if this was the last substituent? There wouldn't be a dash. It would be just parentheses decane.
Okay, so methylpropyl decane.
Yeah.
Okay.
Dashes really, I think, we can probably say come when there's a number to separate numbers. Okay, anything else on the nomenclature page? Did I say much about this page on the video? Did we do these on video? Did we do this one?
No. No, we didn't.
We did those 3?
Yes.
Okay. Let's name this guy here. Question?
I just have a question. If you have like a prefix, like a dimethyl, do you look at the di when they read alphabetically or no?
No, you do not. Hold on. It varies. First off, the nomenclature book's about this thick. You can go check it out. If it's a simple, like just dimethyl, you don't. If it's something that's complex, like dimethylaminoethyl, it becomes complex, then you do. But I don't think you'll see that. The answer to your question is you ignore it and you go with the M. Dimethyl would be considered M.
Yes, sir.
Tri, yeah. Also, if there's any like italics word before, like tert-butyl, that'd be B. Good question.
That's what I was gonna ask about, but, well, I was gonna ask if you're not using IUPAC and you do like T-butyl, so like if you go down to the cyclohexane, if you do one of those and don't use IUPAC, it would change the order if you did like,
It could, because if you use a common name, it would have a different.
so is that okay, or?
Yeah.
Okay.
If you're using common names, you're allowed to use common names. If the common name is sec-butyl, then that'd be B, where otherwise it might have been something else. You would go with the, yeah. Let's see how this one looks. Longest continuous chain, 1, 2, 3. I think we can do longer. 1, 2, 3, 4, 5. Either way you go from here, it's 5 or 5. It's the same thing. So it's 5. Okay, and that's what? Pentane. What's on the pentane? Iodo, chloro, and what is that? Yeah, that's just a little methyl guy, right? One position, which end? If this is it, that would be 2, 3, 4. If this is it, it would be 2, 3, 4. We got another case where it's like we have to go alphabetical.
Which would be one of them, be as close to alphabetical.
I don't remember this one being like this before. Alphabetical I or M? Yeah, I don't remember this. Are we doing this right? Pentane? 1, 2, 3, 4, 5. All right, good. I before M, I mean, I don't know what else to do here. So that means this is, we're going to make the iodine 2. What do we got? 2-iodo? Well, see, you might say, well, shouldn't the chlorine become first? No, because whenever you list it, we don't list it in alphabetical order. No, hold on. Yeah, we do.
Yeah, you would do three.
Yeah,
Two
yeah.
iodo.
And that's why I was confused 30 seconds earlier. We do list them in alphabetical order. But the numbering, once we get the numbering using the alphabetical, then we forget about it. 3, 4. Then we list them, not in numbers, not 2 first, but alphabetical first, which is 3. Because chloro is there. 3-chloro, 2-iodo, that would be lowercase probably, iodo. 4-methyl pentane. Yeah, and we just allowed the 2 to take precedence over the 4. Because if we had started on this end, the difference would have been, that would have been 2-methyl and this would have been 4-iodo. Starting on this end, we get the I coming as at the 2 position.
Why is the chloro capitalized and the rest?
Well,
Is it because it's first?
it could vary, just like a word can vary.
Okay.
If it's at the beginning of the sentence, I'd capitalize it.
Okay.
If you want to give it a heading, I'd probably capitalize it. If it's in the middle of a sentence, you just do lowercase or something. But I'm sort of just putting it up here like I'm capitalizing it like a heading. Okay, and that's it. Your test will be kind of through here, utilizing your halogens. This down here is just a little bit for reference at this point. You see there'll be similarities. We'll actually cover alcohol nomenclature in organic 2. This is a 4-carbon alcohol, 1, 2, 3, 4. The OH is at the 1 position. You can call it N-butanol because it's straight chain. You can also call it 1-butanol because the OH is at the 1 position.
And that's IUPAC?
Yeah, that's IUPAC. Either N or 1 is I would call IUPAC. And I think you used 1-butanol in lab this week, right? Yeah. 2-butanol thus, okay, again, this is not going to be on the test, but hopefully you see it's pretty straightforward. 2-butanol, the OH would be here. 2 position, that being 1, 2. Okay. I'm just kind of giving a little flavor of the other nomenclature. As you go along, it'll all be very consistent, and you'll just look at little modifications as you do different functional groups. Okay? You'll always look for the longest continuous chain, that type of thing. Okay, condensed formula structures. See how we did up top here. Let's see, I see 3 methyls. They must be on 1 carbon. Methyl, methyl, methyl. And this carbon must be bonded to another carbon. And I reckon there's 2 methyls on it. And then we can keep going to a CH2. Then what is this? CH2 to another carbon. And then what? An H and an O? H don't make 2 bonds. So what is this?
OH.
Well, let's look at that then. So you're saying it's a CH2COH?
Oh no, it's double bonded to an O and the H is just.
If it was going to be an OH, I would think that they would just write it OH. No, that's a C. The H is bonded to the C. So we got the CH2C. There is an H there. But we can kind of look at our structure, and the O needs to be sort of what? That carbon needs 2 bonds. Yeah, the O is double bonded to the carbon. And ultimately, what's this functional group on the end there now? Aldehyde. Okay, you can call me Al. Okay? And this over here, your CHO is the common way to condense the aldehyde down. That's how it's written, condensed down. CHO. Carbon is double bonded to the O. Because I reckon if they wrote it like this, then you would have you say, well, was the H on the O? You could maybe figure it out structurally, but this looks more like an alcohol. The aldehyde is like this. How do we do on that one? Aldehydes are condensed down to CHO. Get it right? How do we do? How about the next one? You guys on the right were doing that one, correct? Somebody got this one over here? You got it? What is that at the top? Oxygen? It's only got one bond. Well, typical bonding for oxygen is what? Two bonds, two lone pairs. Also, I mean, I didn't put lone pairs here, but you guys should think about it, because otherwise you end up with something not quite right. Charges, otherwise, yeah. Let's see, I got a CH3 on a carbon, I reckon. Basically, I've got that, CH3, carbon. This carbon is what? Got, looks like it got two methyls on it. Then it comes to, I think this carbon is bonded to this carbon. And what does this carbon have on it? An O, and an H?
I could.
I don't know, because if you look at it, see, all the H's are being shown here.
I did a carboxylic acid.
We'll get to it, yeah. But the way I just did it, if you go back and look, there's no H's on this carbon. Okay? So it's not this. Indeed, what it is ultimately this end is the same as that end. But up here, I decided to put all methyls and just call it 3. Where here, I did it more like this. This endings are the same thing, though. Then we got the carbon over here. It has, to get a good structure, it's going to be like this. Carbon is double bonded to one oxygen, and there's an OH. Here's the take home. CO2H, that's condensed down for what? Yes, that's carboxylic acid. Anytime you see the CO2H, that's condensed down. Now this could also be condensed down to COOH. Sometimes people will write it, instead of saying 2, they'll say the O's separately. Everybody with me? This is your carboxylic acid way it's used. So one of the main reasons I give you these two is because these are two very common sort of end groups that are condensed down in a specific way. Also using the parentheses to denote multiple groups. Everybody good with these? Okay. Now you may see structures like this, but you're going to see a lot of stuff like this, partially condensed down, that you got to be able to deal with. Especially on standardized tests, where a lot of times they don't have enough room to draw out the structure, and they may not have a drawing program, and it's easier to just sort of type this like this. They're giving you structure here. Down here, how many primary CHs in this compound? That is H's on primary carbons. How do we do? Right?
5.
It seems like it's more than 5.
Well, 3 per carbon.
That's a good way to look at it, because each primary carbon, 3. How many primary carbons? 1, 2, 3, 4, 5. Yeah, it's 15, right? How many secondary CHs? Secondary CHs. That's a secondary carbon. There's there. Any other secondary carbon? That's the only secondary carbon in the compound. 2. How many tertiary CHs? 1. And there's no such thing as a quaternary. For a total of what? 18 H's total? Is that 18 H's total? How can you quickly tell? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. It's all saturated, so it should be what? 2n plus 2, 18. Yeah. There should be 18 there. You can count them all up. Okay, intro to di-substituted cyclohexane. If that methyl wasn't there, what's the name of the compound on the board? Methyl cyclohexane. Methyl cyclohexane, right? Okay. Dimethyl. Now that we have 2, though, we can have numbers. Because the methyls can be 1, 2, or they could be 1, 3, or they could be 1, 4.
Does it matter where you start? It doesn't matter whichever number, right?
You mean, could it be 1, 2?
Yeah.
It's the same thing. Either way is a no. Unless we maybe get another substituent. For example, if I had a bromine here, then you would want to be 1, 2, 3. As opposed to 1,
Try to do it in alphabetical.
as opposed to 1, 2, 6. Right? 1, 2, 3 is better than 1, 2, 6? Okay. These are all isomers. They have the same formula, but they have different connectivity. Because here the methyl is connected to a carbon next to the other methyl. Okay? What do we call isomers that have different connectivity? Constitutional isomers. Yes. Okay. But let's look at this. Let's look at the 1, 2 closer. These 2 carbons in the ring are tetrahedral. That means 2 in the plane, 1 forward, 1 back. Well, the methyl could be forward here, but it could also be forward here. This is called cis, because they're on the same side. Now you can also have cis drawn like this. This can be back and that can be back. That would also be cis. Now these are actually the same exact compound. Same exact compound. Methyl's forward and methyl's back. Just like this. Here my thumb is forward. There it's back. Is this the same hand or different hand? One hand. Okay. Forward or back. That's what you have here. Let's look over here. These, the methyl is drawn forward. By the way, what is back on this carbon that's not drawn?
Hydrogen.
A what? A hydrogen, right? 2 in the plane, 1 forward, 1 back. The thing back is the undrawn H. Now this methyl is drawn forward. What's back? What's forward here? Okay? The H's are there, going the other way. I just haven't drawn them in. Here the 2 methyls are not the same side, they're on opposite sides. That's called trans. And you can have trans this way, or you can have trans this way. Now these are different compounds. Similar to how your left hand is different from your right hand. Okay? Now, these are isomers. Does everybody agree? If they're different, then they're isomers. Because they have the same formula, but they're different compounds. I told you they're different. What type of isomers, though? Do they have different connectivity?
Yeah.
Here you might say yes. Why is the connectivity different?
Because the bonds are flipped.
The connectivity is really not any different. Just like my hands. Everybody agree they're different? Do they have different connectivity? I actually don't. I have a thumb connected to a pointing finger. Thumb connected to a pointing finger. We're getting into test 2 material here. These have the same connectivity. So if you believe that, are those constitutional isomers? No, constitutional isomers have different connectivity. Okay. They're not. They're a different type of isomers. These are called stereoisomers. They only differ in the way the groups are projected. Same connectivity, different projection. How do we know they have the same connectivity? Here's how. If you name them, that will tell you the connectivity. What's the name of this guy? Both of these have the same name. They're both what? Name, forget about the bonds. Dashed in bold. What's the name of this? 1,2-dimethyl cyclohexane. Yeah? Okay. What's the name of this guy?
Same thing.
Same. Because they have the same connectivity. Probably shouldn't say any more about this. This will be moving into test 2 when we look at stereochemistry. Why are these the same? That'll be important to know. In fact, when we get over there, we may look back at this page right here.
So cis and trans are both stereoisomers.
That's good. Yeah, cis and trans is a type of stereoisomer. Because look, yeah, every one of these compounds up here has that name. All 4 of those in the row have that name. Thus, they all have the same connectivity. Okay? All right. Let's look at projections. Let's take a 2-minute break, and we'll look at Newman projections.
you're literally right by the goal. So like for half the game, you're gonna get it. The other half, you're gonna get the bottom of the pool pretty good. Come on. Just let me know. Do they have names? Yeah. See it all. I'm a good, yeah, I'm a good They switch, they're supposed to switch in all in July, but they didn't. Switch back to.
I wonder if that's what it was actually.
It's crazy. Oh, the stadium. It's sold out. Like I don't think I've ever seen it that crazy with, and they had a tech game and it was nailed. The game that I
Okay, guys. All right. Conformations. We'll look at conformations of alkanes using Newman projections. We have a variety of things associated with that, including like energy diagrams. And we'll look at conformations of cyclohexanes. That'll be your chair conformations. Okay? This is an energy diagram of ethane. Ethane. Here's a molecule of ethane with all these on the end being H's. 2 carbons. Sigma bond between the carbons so it can rotate. Okay? What we need to be able to look at is a couple of things. What's the most favorable rotamer or conformer? That is, this thing can rotate. Yes, it can rotate constantly, but it's going to prefer one position. Will it prefer maybe here with these two lined up? And what do we want to call that? Some terminology here. Or would it prefer to be more like this, where this one is not lined up with anything? Yeah, that's actually going to be better. What do you want to call that? So some terminology we'll see there. Also, why would it prefer to be like this and not this? Well, because there's a difference in energy. Why is there a difference in energy? Can we plot the difference? If we do a full rotation of this one around, all the way around, how many different energy levels do we come to? Only 2, and it's shown here. Okay? Or the answer, other than 2, it could be an infinitesimal number, because you could say, well, that's different from that, and that's different from that, and that's different from that. But we're not going to do that. We're going to look at precise ones, like the 2 I showed you. Yes?
How would you know, like, which one is considered, like, 0 degrees, and, like, throughout, like, where to start when you're drawing these?
Well, some starting point, and that's 0 degrees.
Okay. Would it also be right, though, if you started, like, with the staggered and said that was 0?
No, because you got to have sort of 2, I think. Let's get into it. We'll see. Staggered is going to be not 0 degrees. Okay, how do we show these on the board? How can I show this right here on the board? That's a Newman. There. Okay, I reckon let's start by showing that. How do we show this on the board? Chemists had trouble. Okay, how do I want to draw this? Because I got to show it to you, or I got to send you something in the mail, or okay, I'm going to write it down. Well, Newman, who was at Ohio State long in the middle of the century, came up with a way to do this, and it's called Newman Projections. We're going to draw it as if we're looking down 2 carbons. So here, you're looking at this. If I'm going to draw it like this, or like this. Here's the first carbon, we're going to have one in the back. Okay? We're going to draw it like we're looking through here. Now we do this with I reckon we're good here. Circle. Okay? Circle, circle, dot, dot. And a circle in the middle. Okay, a little dot in the middle. The dot in the middle is going to be the first carbon. Okay? I'm going to turn the back a little bit. We're going to draw this. The first carbon has an H going straight up. Now, I say straight up. It's not exactly straight up. It's actually leaning towards you. We're going to call it straight up in this diagram here. Straight up, and it's H. Now we have an H going to the right. Yes, all these are a little bit towards you. A little bit to the right, but also a little bit down. So like this. And the other H coming over here, also a little bit down. And that's the front carbon. Now we're going to look at the back carbon. Now the back carbon you're not supposed to be able to see. It's behind the front. So you're not supposed to be able to see it. It's like it's back there behind it. It's almost like this here's a circle. But you can see the H is coming out back there. And so that H is coming out going like that. And so you draw it from the edge of the circle. It's like the thing it's connected to is back there behind all this. But then what? Back carbon has one straight down. And the back carbon has one going off like this. And there you go. And that's supposed to mean something to you. Okay? When you see that, okay. Now we're able to put it on the board. It's called a Newman. And that one looks like which one? I mean, it looks like this guy here. Okay? So let's look at that. The back is down and the front is up like that. You see? And that's what we drew here, yeah? Now this is an energy diagram, potential energy. This is just rotation here. This is lower in energy than this. What is that up there? That's where, what is moved, the front or the back? Yeah. Throughout here they're rotating the back carbon. That's where it's like that in the back. It's straight up just like the front is straight up. Okay. When they're straight up, ideally you're not supposed to be able to see the H behind it because it's like the sun in front of the moon. Eclipsed. Okay? Can you see the H behind? Not if you were like exactly lined up. But when we draw it, we draw it a little bit to the side because if it was right behind it, you wouldn't be able to draw anything. So this is supposed to denote eclipse. Let's talk about terminology. Right here, these bonds are eclipsed. If I rotate the back here, there's nothing no longer eclipsed. It's now like this, and you can see it. That's called staggered. Makes sense, yeah? Now we got the terminology that everybody can be using. Eclipse, staggered. Which is better? Which is lower in energy? Well, you can see here. Lower is what?
Staggered.
Staggered. Why is staggered better than eclipsed? Well, it turns out that when it's eclipsed, these electrons are just interacting more. Because they're bigger, they're clouds here a little bit, okay? And when you turn it, it does give more room. Okay? Less electron interaction here, and that lowers the energy. Because when you bring electrons together, they get a little nervous, a little higher energy. All right. So we start here. We're rotating the back here, and then rotating it. You really can't tell, but let's rotate it to the right. So as we rotate it, We're getting lower in energy until there. That's actually the lowest point. Now these in between, this is where we were rotating. We're not really going to give this name. This is like infinitesimal. When I say how many energy levels, it's like discrete energy well levels. Here and here. Now if we start rotating it again, we're going back to what? We're going back to eclipsed. And so we went back higher. Maybe I should change this back. These are all still hydrogens, but I'm rotating. Okay? I'm rotating eclipsed. Rotate. And we get staggered. Continue to rotate. Now we're back to eclipsed. It's just not the same H. It's different H. But an H is an H, and it's the same energy level. Now we keep rotating the back, and we get what? It comes back down, staggered. Then we keep rotating, and we're going back to eclipse. And you can't get any worse than just fully eclipsed. Because if you keep on, you're starting to separate them and making them staggered again. And now we come back to boom. And now we're actually back to the very beginning. And that's just a repeat. And a common question here is how many different energy levels do we go to? There's only two there. This energy level and that one. That's just a repeat of that. That's okay. These are just repeats and these are just repeats. Two discrete energy levels. Staggered and eclipsed. I don't do anything with math or calculations. How much the energy is different. I don't do anything with
So to understand what's happening.
the terminology, what's going on. We'll see other terminology. For example, this. Someone asked about the angles, dihedral angles or torsional angles. Okay, let's look at that. A dihedral angle, two planes. Okay, two different planes. Dihedral angle is the angle between one bond in this plane, assuming these are straight up. Okay, and then the bond in another plane, assuming they're kind of straight up. Right there, what's the angle between the two? 0 degrees. Okay? Now maybe you'll get here. What if I turn that here? Okay? That is, the back is straight up, and this guy is like that. But see, it's this, I drew it in one plane. Here it's two planes. That is like that, and the line that's going this way is not in the plane of board, but it's just out. It's two planes. But you can still see the angle that it's straight down and then straight that way. And if we just move this back, then it's one plane and the angle's the same. But that's 90 degrees. That's called a dihedral angle. Oh, it's two planes. Okay? So look, what's the angle here? Well, no, they're both straight up. There is no angle. As we start turning, we develop a dihedral angle. Now when we get here, well, they're turning the back. So let's keep the front the same and let's turn the back. There. What's the dihedral angle between, let me make it green, between the front H and that?
45 degrees.
Or we can just make them both green. There the dihedral angle is 0. There it is 90. But that's not a good staggered. Staggered is more like that. What is the dihedral angle between the two greens?
45.
If we do it in one plane, it would look like kind of like that. That's in one plane. The greens. What is that angle?
45.
I don't think it's 45. Because think about it this way. This is how I have to think about it. That is, what if it was there?
180.
180. Everybody agree that's 180? Yes, because halfway would be 90, 180. Okay, but look at this. If we do boom, that's one rotation. Boom, that's two rotations. Boom, that's three. Three rotations to get to 180. So each one was 60. Yeah? 180 divided by 3. Right? That's, if that's, I'm doing 3 equal rotations. So divide 180 by 3, it's 60. I mean, we could get out our, is it protractor, compass? What is it called? We could get, it's, okay, here it is. It's 60. All right, but that's how I remember it because it's a third of all the way to 180. Now, maybe I didn't draw it exactly 60, but this dihedral angle here is 60 degrees. Okay? What is this dihedral angle?
60 degrees?
It's also 60, and this one is 60. And if you add up all these 60s, you get a total of 180. And you see, yeah. So there, did that answer anything over there? You asked something about angles at the very beginning.
Yeah.
All right. Let's go to butane. Butane. For butane, I'm going to take these off, and we're going to do it like this. 4 carbons, 1, 2, 3, 4. The H's on the 2 center carbons, I'm just going to leave as these little small nubs. I'm not going to put anything there. Butane. Okay. Now, I think down here, I'll pull it up. The Newman projections are shown down here. Let's see what we get here. This is where the methyls are both what? Eclipsed. What do you think about these being eclipsed? High energy, low energy?
High energy.
It's not good. Eclipsing is a bad interaction. You'd rather these be apart. Start here. There's your energy. You see how the A is higher energy? Let's rotate here. Here I think they're rotating back or front? We're rotating the front here. So let's rotate this 60 degrees. And we get this guy. Dihedral angle 60 degrees. It's no longer eclipsed, but it's now staggered. We're going to come back and give it a special type of name for that one. Rotate another 60. We get here. This is where the methyl in the back is eclipsed with an H here. Eclipse is never good, but there's a difference. Which is worse, the methyl's eclipsing or a methyl and an H?
The methyl and H.
I say which is worse. Which is better would be methyl and an H. So you've got 2 different eclipse forms, but one is worse. So A is higher in energy than C. Here's a take home. Your eclipsed are always going to be higher than staggered. But you may have different types of eclipsed, which vary. And it's worse to have methyls eclipsed than a methyl and a smaller H. But it's still eclipsed, so it's not as good as this B was, which was staggered. We keep on going. We're rotating the front 3 times to a dihedral angle. The methyls are now 180 dihedral angle. It's like this. That's staggered. You see the front, the H's are coming staggered. But look at these. This over here was also staggered. But this one's better. Why? That's staggered versus this. There, even though it's staggered, the methyls are still here. This way, they're totally opposite. And that's the best. And we can give terminology. That's called anti. Your 2 big groups, or the two groups of consequence, are anti. Anti is a special type of staggered. It's usually your best. But sometimes you may have multiple antis if you have a lot of groups here. Then you have to say, well, which anti is best? Here there's only one anti. Now we can go back to terminology. Both of these were staggered. We call that one anti. What do you want to call this one? It's called gauche. I think that's German. German for to the side. Versus the methyls. The methyls are staggered, but they're kind of to the side of each other. It's just turned to the side. It's a type. It's a special type of stagger called gauche, where the dihedral angles between your groups is 60 degrees. They're anti. Now if we keep going, by the way, all those four have different energy levels. A, B, C, D. You see how D, which is fully anti, is better than gauche? Now we're just going to kind of come back and start repeating. Here, the H and the methyl are eclipsed, but it's not as bad as, now this is not written. I sort of call it this. I don't know if it's official. I call that partially eclipsed, with the methyl in the smaller group. I call it, what do you want to call that? Kind of like fully eclipsed, with two big groups eclipsed. Here, but these become, yeah, these are both here. They could almost give them the same letter. We're going back to C. Then we continue on, we get to staggered, the methyls are gouged to each other. That's F, that's just like B. Then we come back to fully eclipsed, back there. So, the previous one we had two energy levels. How many here? Again, I wish they had not have used. Yeah. Your A's are the same, the C and the E is the same, that's 2. The B and the F is the same, that's 3, and then D. There's 4 energy placements. So butane has 4 different energy levels, discrete energy levels you can get to. Some miscellaneous things here, and then we'll see what type of questions we have, and then we'll this is the eye looking here. Okay, I can have this compound. Okay, we can go back to putting, just calling these H's, 2 carbons with all H's. Let's look at this. Each carbon's tetrahedral. 2 in the plane, 1 forward, 1 back, right? Let's see. This carbon over here. 1 bond in the plane going over here, the carbon, the H coming straight up in the board. But then you have an H forward and an H back, right? So this is how it is on the board here. And then the carbon over there, the H that's in the plane is what? Down. You see it's down. And then you have 1 forward and 1 back. So there it is on the board. That's called a perspective drawing, where we use the dashed in the bold. Okay? You can also have what's called a sawhorse. I don't use those much. You occasionally may see them. They're trying to get some perspective there. It's like it's up like this. But instead of showing this here, they've kind of turned this and drew it flat on the board. Okay? And then it's like this H is going sort of right between those back there. You can kind of see that a little bit. I'm not going to use those much. It's called a sawhorse projection or representation. How did we draw this? Didn't I look down? I just turned this way. I was looking down, just like on the board it's showing you the picture. And what did I see? I see a carbon in the front. Come over here. See a carbon in the front with an H going straight up. See, that's what I drew. Okay, they're just showing you a little bit how you get there. We kind of already had done that. This is sort of the sawhorse showing that H splitting. Okay, all this is just all in your book. Sometimes you see these sort of space filling models where it gives you more of how much space the group takes up. This is butane with the methyls fully eclipsed. These methyls are really close together. They're kind of clashing here, okay? They're really bigger than just the CH3 we draw on the board. It's a little better for them to be gauche. You can maybe see that, but it's best when they're anti. You kind of see that. It's pretty much just some miscellaneous stuff there to look at. We're missing something. No, we're missing a handout. I thought it was in that one. It's not in that one. I don't have it. We're missing an outline. We're missing an outline. Yeah. That's what we're missing. Dang it. Dingity ding ding. Time we go. Yeah, I need to go get the outline. I apologize, guys. Let me give you a problem to work, and let me go get the outline here. Let's see how we can do here. Draw the most stable Newman conformation of this compound here. Looking down, the 1,2 bond. I'm sorry, not the 1,2 bond, the 2,3 bond. The 2,3 bond you would figure out by just nomenclature. Okay. All right.
Yeah, and that's what but I usually tell which ones from old guys. That's how it is. And what it's from some night brush.
Okay, the top text part of this we've covered. And we were ready to start with the 3 compounds. Instead, I'll give you this one here. Let's look at this. How do we deal with this? Perspective, how do we look at this guy? What did I say, a 2-3 bond? What's a 2? 2-3. Okay, so looking down that with so we want to stand over here and we want to look through there. And carbon 2 is in the front. Okay? Carbon 2 is here and carbon 3 is behind us. Okay? I mean, you can make a model, but I want to just kind of do it without models. Maybe the first one we'll do. It's called bromine green. Okay. This methyl is coming this way. The bromine is coming towards you, so I need to disconnect here. Like this. And then we go down here, zigzag. This is a fluorine. Fluorine, that's called fiery red. It's going back, so we need to make it like this. Zigzag. I got another carbon coming there. I can slip it on maybe. I have another. It really doesn't matter. That's going to be just sort of the 2-3 bond is what really matters, but we got that there. Okay. Now this guy has all types of rotations. All types. What's the best conformation? Show that in a Newman. Here's a starting point. Green. Right there. Okay. All right. First, 2-3. Here's the first carbon. What do I see? I'm just going to turn so you can see what I see. Here's the front carbon. But I'm going to do it out like this because this is your paper. Now, actually, your paper is easier because I can't turn the board, but if you were holding your paper, you can turn it and look down the side of the paper. Let's do it like this. I see a carbon. What's coming straight down on the carbon, toward my feet? This methyl group. Look, you don't believe me? Look. There it is. Okay? Now, it's coming towards you, yes, but maybe it's going straight down, the methyl. Okay, it's coming straight down. There's my feet. So on the front carbon, I got a methyl coming straight down. Bromine's on the carbon. Is the bromine, if I'm over here, is the bromine going toward you guys or to the hull? Clearly it's going toward you guys. So is it on my right or left if I'm standing here? Right, correct? It's on my right. The green's on the right. Went up a little bit. The bromine is here. What's on this carbon going behind the border? The nitrogen hydrogen. There it is. It's a little nub there. If I'm over here looking, that is going to the left. Well, it's H. There's the front carbon.
For drawing the Newman, does it matter which is the H and the C in this case?
Does it matter what?
Placement of the H and the C matter? Or would it be the same if they were vice versa?
I think it matters. The methyl is down here by my feet.
Right.
I mean, here's the feet. It's pointing to the ground. I mean, I think it matters. The H is going behind the board. Because if we drew it in, it would be dashed. If I'm over here, behind the board is my left. It's like this is the board. And you guys are sitting down here. The bromine's coming towards you. The H is going behind the board. That's the front carbon. There it is. Now let's look past 2 and see carbon 3 back there. I see something going straight up in the plane of the board. What is it? It's not the F. The F is coming, going behind. What's in the plane of the board straight up? Well, it's an ethyl. It's a carbon with another one. straight up. And it's got another one on there. I don't know why none of these are going right. I mean, that can keep going as long as whatever. We're just worried about carbon 2 and 3. What's on carbon 3? How's the F? Towards you guys or behind the board? If I'm over here, I didn't draw the little man on that side. I'm over here, just like I'm standing here. If the H is going, if the F is going behind the board, I'd be on my left. What do I see? But it's also coming down. And it's over here. What's on this H coming towards you? Towards you?
H.
And I'm drawing hydrogen. If I'm over here and something's coming towards you, it's on my right. Now if I'm over here and something's coming towards you, it would be on my left. But I'm over here because I'm going to look down to 3. H. There we go. That's how it's drawn on the board. But is that the best conformation? No. What do we want to achieve in the best conformation? What was the best with butane? The methyls were anti. Well, what's the broad concept over there? Your biggest groups were anti. That's the main concept. What's the biggest groups on the first carbon? Now you might say, I made up this on the fly. Sometimes I design them so it's easier to decide. Are you a bromine or methyl? A bromine's bigger. Bromine's bigger. Okay. What's the biggest group on the back carbon? Yeah, bromine's bigger. The H's are almost negligible.
Yeah.
Okay. I'll try to make sure I give you ones that are easier. For example, if they're all alkyls, you know a butyl is bigger than a methyl. If they're all halogens, bromine's bigger than fluorine. Okay, on the back carbon we have an H, ethyl or fluorine. Which is bigger? Ethyl. Yeah. There are your two big groups. What's their relationship to each other? Are they, first off, are they eclipsed? No, they are staggered. But what do you want to call it? Terminology. They're kind of a little bit to the side of each other. We call it gauche. Right now the two big groups are gauche. Is that the best, or would you rather have them anti? Yes. We can rotate this guy. Just like this. Here it is on the board again. Bromine. That's how it is on the board. And there it is drawn on the Newman. And you see how the bromine and the ethyl in the back are gauche? Now there they would be eclipsed. But that's how it is on the board. They're gouged to each other. Bromine is green. We want the bromine and the ethyl to be what? Anti. That is the most stable conformation. We'll draw it here. But back over here. That is, when this thing's rotating, it's all doing this. But is there a certain one it would rather be? Yeah. These guys are going to tend to want to be anti to each other. It's going to be more like this.
So does it kind of speed up around everything else and slow down around the part that it likes?
You could maybe think of it like that. It's going to favor what it likes, so it's the lowest energy. And if it was some reason, you'll go, ooh, I don't like that. And it become, you know. What we're looking at is the most favorable conformation. How can we show this here? The front carbon can just rotate. Everybody with me? Front carbon can just rotate. That is, I can just move this bromine down and redraw it. I'll let you redraw it. Redraw it with the bromine and ethyl anti.
Could you rotate it
You could, yeah, either way. Either one. As long as what you show is the bromine and ethyl anti, then it's good. It's just like, can I show you like that or like this? It's the same answer.
How do you know that the ethyl is bigger than the fluorine?
Look at the weight.
Is that the weight?
Well, which is bigger, carbon or fluorine?
Fluorine. One fluorine is bigger than carbon, right?
No.
The size goes that
Size this way. Yeah. Even though the molecular weight, atomic weight is higher, it's because you get, with more electrons, it starts attracting more unhedging chemical on the diamond. Yeah. But also you've got two carbons. And so the ethyl group, just look at it, it's bigger. Again, we'll clarify some of this. Well, I mean, circle, circle. The back we didn't do anything to, right? I rotated the front. There's the back. Now the front, I had the bromine down now. We're just turning this. If the bromine comes here, where does the methyl go? The methyl's going to go here, and the H turns over there. And so now we have that there. Now we have it in the most stable conformation with the two big groups being anti. Yeah? But now we can assess it. And maybe we could say, what's the relationship between, in the most stable conformation, what's the relationship between the hydrogen on carbon 2 and the fluorine? What's the relationship? Positioning. They're anti. You can answer that. What's the dihedral angle between the fluorine and the bromine?
60.
Yeah. So now you can answer questions about the most stable conformation. Okay, there's others to work there. Please work those and we'll look at them on Tuesday. Question?
Wouldn't you not want the ethyl and the methyl to like interact?
Good, yeah. The ethyl and the methyl are gauche. So you're saying you'd rather make sure these are anti? Well, when these are anti, now you have your bromine in your ethyl gauche.
It doesn't like the bromine is more.
The main thing is you have your biggest groups anti. That doesn't mean you're not going to have something interacting. You just stuck with that. There's no way to not have that. Biggest groups anti is going to be usually the best. We may come up with some crazily substituted where it's not. For us, biggest groups anti.
I have a question about the test. So everything up until today, so whatever we learned Tuesday is going to be test 2 material, correct?
No, Tuesday will be
Oh,
test 1.
okay.
We have to finish up this here. The last topic is the please look at the remainder of that. There's also, on the flip side, homework. We're naming this. Can you name that compound from the Newman projection? I would recommend taking it from the Newman back to the line bond. Please look at that. Okay. Conformations of cyclohexanes. Let's look at that. Cyclohexane, 6-membered rings. How do we draw those on the board? Here's a 6-membered ring cyclohexane. When we draw this on the board, is it flat on the board? Well, first off, it has 2 H's on each carbon. But is the carbon backbone, is it flat? actually not, because each carbon is tetrahedral. Okay? It's not flat. If we made it flat, is all the carbons flat, if I can make it like that, it would be like that. Try to make it just flat. The H's are one way and the other, they have to be like that for tetrahedral. Is that best? Actually, no. A couple of reasons. First off, if it was flat, the adjacent H's, would they be eclipsed or staggered? There they are.
Eclipse on two sides.
They would be eclipsed all the way around if it was flat. Also, to make it flat, this bond angle, what's the bond angle between the carbons? 109.5, right? To make it flat, you actually have to broaden the bond angle out beyond what it wants to be. But if we pucker it a little bit and pucker this, that's how it exists. Not flat, but one end this way and the other end that way. And that's called a chair conformation, because if you can see it, I wish I had larger. It's like you sit here, your feet can spill over here, your legs spill over, but then the back is here, like a chair. Now, you could have the other end flipped up as well. That's where four of them are in the plane, but then the top and bottom are both forward, or both up. What's that called? That's called a boat. Now, the boat is not good compared to the chair. Chair's the best, and that's what we'll focus on. The boat gives what's called flagpole interactions. These two H's start interacting up here, called flagpole. So instead, this rotates down. Okay? Now, it can't just spin because you can't break the ring. So for these guys, you have your chair conformation. But how do you draw these? I know we're pushing on time, but let me see if I can get you started on just draw one of these. Okay. We need 6 carbons, and we need sort of a 3D view. We're going to draw 2 lines sort of parallel and will offset like this. And that's actually 4 carbons already. We want to connect these 2 with carbons, and we do that with a point like this. And then we connect these with a point. Now, the first time you do it, you may get it perfect, or it may not be so perfect. There are your 6 carbons. Mine's not quite as perfect. I wish this wasn't quite as deep here. But you sit here, and here's the back, and your legs spill over. A lot of times books will kind of show a person here, the legs spilling over. I can't draw worth a hoodlum. And there's laying here, legs spilling over. There's the backbone. Okay? Please allow me 2 minutes here, and we'll get one drawn. H's. Each carbon has 2 H's. You got up carbons. This, and this I call up carbons. They're kind of like up. These are down carbons here. Up carbons get straight up bonds. Up carbons get straight up bonds. We draw those like that. The other 3 I call down carbons. They get straight down bonds. You kind of draw it like that. You're kind of developing a 3D, like this is in front of that. Those are called axial hydrogens. Okay? Axial hydrogens. Straight up, straight down. The other H on each carbon is going to be called equatorial. It's going to be around the midsection like the equator. These are a little bit tougher, but it's straightforward. This is going to be like this. This bond is going to be parallel, not the one that is not to one that's connected, but the next one, or that one. This is going to be parallel to these two bonds. This one's going to be parallel not to that bond, but to this one. And they also never come internal. They always go away. So this is going to be parallel to this. So it's a little bit up. And these are supposed to be parallel. So this one is what? Can you draw that one in? Parallel to this. This one parallel not to that bond, carbon-carbon bond, but over here. So it's almost going to look, see, I wish this was a little bit more slanted, but it should be equatorial. You got to know that's equatorial because a down carbon has a straight down. And there you go. You got a chair conformation on your paper. Okay? You have axial hydrogens and equatorial. What do we do? What do we miss? Right here? Parallel to what? Not this one, but not that one, that one. And so kind of like that. Yeah? There you go. Okay, please be making some progress on this handout here. Including this variety of questions to be working. Reading, there's a variety of stuff I'll introduce and tell you about and discuss. Please read, but then working problems here. If it says to do anything, attempt to do it. We'll be here on Monday, yeah? Please have a safe weekend. See you Tuesday morning. Test is on Wednesday. This is our last handout here. Have a good week.